So Nino is a senior researcher and lecturer at ETH Zurich at the Computational Social Science group. And his main interests include obviously, well, complexity in data science, but in more particular, this means dynamical processes, so network, predictive analytics on financial technologies such as cryptocurrency and blockchain markets, and machine learning, social network analysis, network dismantling, Monte Carlo algorithms, etc. So besides ETH Zurich, he was also working at the Ruđer Bošković Institute in Croatia and Faculty of Electrical Engineering Computing in Croatia at University of Zagreb, where he also earned his PhD degree in computer science. Nino was also a visiting researcher at Robert Koch Institute in Berlin and Courant Institute of Mathematical Sciences in New York, his PhD degree. So I remember Nino back from university days. He was still he was already giving lectures about this spatial epidemics and complex networks in charge of estimation and modeling Nino back from virus spreading all over the area. They later learned that we were doing this already in high school days. That was very nice. But the last time we met, it was very nice coincidence. We met in a rent-a-car kiosk in San Diego. So that was fun time. So just if you were wondering what Nino was driving, yeah, it was a red Ford Mustang Cabrio style.
Thank you, Vinko. Thank you, Vinko.
And Nino, when I'm reading your biography, it really seems that you were leaning on this commercialization of research back from your old days. And I'm glad to see that you have finally succeeded with your company, ASOT, if I'm pronouncing it very well.
It's okay, yeah.
Okay, you will tell more about it.
Yes.
But what I see is you are applying all this knowledge into financial market in Switzerland, with the headquarters in Switzerland. The company was started by 3 of your colleagues at ETH Zurich. Well, you and 2 others. I think Steve is one of them, the CEO. Stefan should be also here with us. So thank you guys for holding this session. And Nino, the audience is yours.
Okay. Thank you, Vinko, for such a nice introduction. I will also try to speak a little bit at a slower rate, because I also know that sometimes during these video streams, it can get hard if people talk at the full speed. Vinko, you're hearing me well?
Yes, it's perfect.
Okay, so let me proceed. So the idea is somehow, Vinko already did it in the introduction. So I will just directly jump into the outline of today's talk. And at the end, I would like that you really don't be shy and that you can ask whatever questions you want. Okay, so around the outline of today's talk is actually I wanted to first give a brief introduction to the complexity science, what it is, because complexity science was part of my actually title this talk. I assume that everyone knows what data science is. So after this first initial part, which is introduction to complexity, which is going to have a lot of nice pictures, then I will also try to go to something that I'm doing. And this is actually, I picked like 4 different topics that are from complex systems or complexity science area. And at the end, I would like also to mention one of the let's say commercial activities or startup activities that we are having, and also tell you why it is an interesting area to be in. Okay, so the title of this slide is complexity, complex, and complicated. So all 3 words are somehow very similar. So I will say at the start, I will try to define all the terms. So when we say that we are studying complex system, this is the definition that I will use. So what is a complex system? So complex system is a system that is composed of many components and which may interact with each other in a dynamic way. And usually it is said that they are interacting in a nonlinear way, and that this somehow can give rise to the collective behavior. So now this is somehow a working definition of a complex system. And as you can see, it is not too formally defined. And when I'm saying complexity science, somehow it is also a synonym, but complexity science is more like approach for studying these type of systems. And at the end, when I say complicated, this is a third word, but usually we distinguish complex and complicated because we say that the airplane design is a complicated, so it's an engineered system. But what we don't want to have is that this airplane somehow is having some kind of an emerging or collective behavior. So he somehow needs to be designed and controlled in very specific and engineering ways. And usually complex systems are something that's that we are seeing in, let's say, our daily lives. So I will now give a few examples of complex systems. In this first figure, you can see people. Yes, these are people. They're crossing streets. As you can see here, they are doing it in kind of different ways. And usually this picture wants to represent that actually humans and social systems, they are also prototypes of complex systems. When we are saying that they are prototype, it means that like usually they are having some kind of an emergent behaviors. There are also a lot of ecological systems, or here there is like some kind of a system of ants that is usually described as a complex system, like flocks of birds. Also, for example, something that can be described with structure of complex networks is protein-protein interaction. And at this point, slide number 8, I'm just trying to show you the headlines of The Economist, and it was actually the special report from 2010. And what is so interesting about this special report, it's saying a world of connections, special report on social networking. So during that time, 2010, social networks were already much more present. And actually today we don't need anymore to describe what social networks are, but all these things around the theories, how graphs are evolving, it happened quite before the existence of these online social networks. This is also one example of from actually it is one headline from a science journal where you could see like a nice illustration, and it's actually going to the direction that now these social media have become so ubiquitous that now we also have to do some kind of a protection. Here actually it was with respect to the social science that we have to protect social media manipulation, and the idea here was around actually political elections in the US, because as we have seen or you have heard before, there were quite heavy use of different, let's say, scientific tools to steering down, let's say, the complex system. And in here, these are the votes. As a last example of a complex system, I would take a financial system. Okay, as you can see this picture. So it says just a normal day at the nation's most important financial institution. And what you can see is actually some kind of an information spreading or rumors. So at the beginning, you had some kind of a message which says, I've got a stock here that could really excel. Then someone else heard really excel, sell, 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 sell. And then you are having some kind of a herding behavior of selling. After some time in the bottom part of this picture, now you are hearing sell, 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 sell. And then someone says, this is madness. I can't take this anymore. Goodbye. Here is goodbye, bye, bye. Then bye, 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 bye. So this is a nice illustration, which is also showing some kind of herding behavior movement that are actually quite also present in complex systems and as such in financial systems. This is actually the reason why financial systems, because they are also quite a good example of complexity in complex systems. So for someone who is more interested in complex systems, I will give you a nice survey from 2010, actually. It is from Mark Newman, one of the pioneers of let's say, complex network approaches. And in this actually survey, you have different approaches. What is the description of complex systems? So let me just give you like a flavor from this report, and it says the following: the general theory of a complex system, at least by Mark Newman, it consists of the several fields. And this is actually a nice point where you will see that study of complex system is not somehow uniquely defined. So I will just pass through these topics and then maybe put some of the comments around this. So the first one is like lattice and networks. So this is some area and theory that is describing actually graphs, graph theory, random graphs, and more complicated structures of networks. And you have a theory of dynamical systems, which were pioneered by actually a physicist. And here you are talking around certain differential equations that are describing systems that are evolving in continuum of time. Afterwards, you have something like similar, like dynamical system, but that is evolving in discrete time. And here you have a prototype cellular automata. Fourth part here is scaling and criticality. So scaling and criticality, it's actually one area where which comes from statistical physics and condensed matter, and usually it is this is a part of statistical physics that tries to describe critical behavior and critical behavior around the phase transitions. For example, when a system is passing from one phase to a different phase. So in statistical physics, actually condensed matter, like you have water that is like up to a certain critical parameter, it is in one shape, it's liquid, and then after this critical parameter, it goes to a gas. So the statistical physicists were trying to apply the whole arsenal or like artillery of statistical physics in describing also the complex systems. Because statistical physics is actually describing systems that are composed of a very large number of particles and is able to have like a statistical description of this system. Although their in particular interactions are very hard to analytically compute for a whole system. Then you have something that's adaptation in game theory. So actually complex systems are adaptive. So one very good example here is spreading of epidemics. So when you are hearing or seeing the evolution of epidemic spreading at the same time, you are adapting your behavior. So here there is also a nice theory that comes from actually, that originated from Nash and John von Neumann. It is actually a part of game theory. Here you are also seeing part of information theory that is actually quite, which originated from Claude Shannon, and actually that people in engineering are using quite a lot. It is also being used to study complex systems. Here we are also having computational complexity. Here, computational complexity is actually describing the complexity of the algorithms. Nash and so all the computational classes, part of game and actually these computational classes then are having some kind of intrinsic properties for understanding of these systems. And finally, we have an area of agent-based modeling, where people are more or less using, let's say, Monte Carlo simulations and different kind of simulators in order to try to describe microscopic dynamics that can explain some kind of macroscopic properties. So as you can see, this is quite a big field, and it's like not unified. So people are coming from different disciplines to study complex systems. And now, where I have done a proper introduction of what a complex system is, I will now go back to the title of this talk, which was actually Interface of Complexity Science and Data Science. So complexity science is defined, at least for this presentation, is like an approach which studies complex systems. So from certain perspective, this is the synonym to complex systems. Data science doesn't need any appropriate introduction. And on this figure that I have actually made, I just wanted to somehow abstractly illustrate some kind of a concept that are coming from complex systems. I would say that this was part of left part of this abstract picture. And here we are having some kind of an abstract machine that could be, for example, Turing machine. And here we are coming to, let's say, an area of data science, where by using data, we are trying to infer something around, let's say, systems that are evolving in continuum. What is very important is this report that I showed you from 2010 from Mark Newman. Actually, it is now being very, some kind of a revolution is happening because of the success of machine learning. It is actually now having a significant contribution to all aspects of complex systems. For example, here, when we were talking about the game theory and adaptation and age-based modeling, you can think of the one part of machine learning that is involved in trying to describe how independent agents can learn. And actually, this part of machine learning then comes and is called actual reinforcement learning. Probably you have heard around the very large success of DeepMind, which actually made significant breakthroughs on reinforcement learning software or like algorithms that are, or learning systems that are capable of learning by themselves. And also they are capable of beating, actually surpassing even the limit that was for very complex games. That was the game of some kind of, for example, Go. When I'm saying here complex, now I'm talking about the number of possible permutations or number of possible moves and a player in this game can have. As you can see, this was also featured in Nature. And yes, so I would say that this reinforcement learning is just one part, how it is entering. It's not just entering the games, it's entering also the finance and how decisions are being automatically done on financial markets. Having showed so many beautiful applications of machine learning, I would invite someone who is interested also to read this actually commentary report that was published in Science, and it's actually showing a bit of dichotomy between something that is usually being said that it's AI, and researchers who are claiming and showing that actually we need more understanding around. Although we are having quite a good understanding, still there is quite this research field is quite open for new insights. On this picture, you are actually seeing some kind of what is underlying in machine learning, the backbone or like algorithm that is driving everything. Is somehow this you are seeing some kind of a landscape, so it's some kind of objective function that is quite complex. It's having a lot of minimums and maximums, and then here you are seeing some kind of a black pot. This black pot is, for example, describing some kind of dynamics. This dynamics is a gradient descent, and this gradient descent is trying, for example, stochastic gradient descent, and this dynamics is trying to find, let's say, some kind of a minimum. With this picture, the previous one, I can conclude the first part where I did the introduction to complex systems and where I showed how some kind of a new interface, so it means the boundary between complexity science and data science, how it is actually being happening today. I will now go to the second part of my talk that is going to be involved around some of selected work for my research, where I will try to show how part of my research is being, with my, of course, collaborators, is being used to push further some kind of an insights in complexity and data science. This is divided to 4 different points. As you can see here, we are having different, I on purposely put different formulas here so that we could see a big picture, because mathematics is giving us an ability to very efficiently encode very complex ideas. So I would describe first this slide. So G, V, comma, A, this is some kind of a graph. So this is a network. So what is the connection between network and complex systems? So usually network, which is defined with set of nodes and set of edges. So V is the set of nodes, E is the set of edges. Usually they are being defined as some kind of, it's just simply a graph, okay? And the first problem, how it is connected to the complex system, is actually that structure of a lot of complex systems are being described with networks or with graphs that are having some kind of complex properties. Okay, so now you understand what is the description of letter V, letter I, and also the letter G, which stands for graph. That is just a tuple of these 2 sets. So in the first problem, we are somehow trying to say how can we transform a graph to a different graph with respect to certain constraint. Here, we are talking about dismantling. So I will tell you briefly what dismantling is. Dismantling is a way how we can disrupt the functioning of some network. So the first problem is connected how we can change a structure such that we can disrupt a structure. And then by disrupting the structure, we can also disrupt the function of this complex system. Second problem is connected to a problem of embedding of graphs. So what is embedding? So graphs are, you can say, some kind of topological objects. So they are not directly embedded to any geometry, to any space. So when we are saying that we are doing the embedding, it actually implies that for every node, we want somehow to assign some kind of coordinates. So if we are in 2 dimensions, then for certain graph, for example, that has 10 nodes, we want to assign X and Y coordinate to every node. Of course, there is some kind of constraint that we want to preserve. Third problem that I will talk is a problem how structure can tell us something around market dynamics. So for here I'm using a different symbol. So for microdynamics, for dynamics, I'm using a blue color, which is here I'm showing some operator of derivation with respect to time. So we want to find how structure can tell us something around the dynamics of a graph. So here we are talking about Bitcoin structure. So network structure of the Bitcoin. And finally, also I can tell you how we can transform a problem of dynamics, for example, dynamics of epidemic spreading, how we can transform this problem to a problem of graphs. So this is the initial problem from which we start. So this is somehow a big picture, and now I will try to represent in some way these 4 topics, and you see that all of them are somehow connected with respect to the structure of a network, with respect to dynamics, and somehow with respect to machine learning and data science. And you will see for everyone, we will try to see where we are having every of these components. So let us start with network dismantling. Before I continue with this, I would just ask Winko can you confirm, is my voice and current progress okay with respect to the audience?
Well, I can only speak for myself, and it's very good. And you can proceed. You
Okay.
can forward a little bit faster if you like as well.
Okay. Okay. Thank you. So we are now talking. We will be talking about network dismantling. So here you are seeing some kind of a network structure. This is actually a network structure of airplane networks. And this is actually one commentary from Nature that is showing that destruction of network was perfect, like perfect meaning that new algorithm was invented, how we can solve this NP-hard problem in a practical way by using some kind of methods from physics. So as you can see, problem is the following. You are having a graph. So if you are removing, how to remove some subset of nodes such that this graph is collapsing. Collapsing actually means that after we remove some subset of nodes, that the giant connected component is below some threshold, so that the largest connected component is sufficiently small. So at that point in time, the assumption was that when we are removing certain node from a network, was that actually all nodes are having the same cost. And then we started to analyze this, and we asked ourselves a question: is this a valid real-world example? So is it valid that that all nodes are having the same cost? And we said, okay, let us try to generalize this by taking the weights into account. It means that this cost can be like actually energy that, for example, you need to take to remove certain node, or amount of money that you need to insert that you remove it, etc. So some non-negative weight. Okay, and then what we've seen is that now some network that is, for example, shown here, we try to remove a different set of nodes. So here you are having blue, green, and red colors. So different colors are results of different removing of algorithms. So the previous algorithm that was like state of the art was actually the red one. So this is the set of nodes that we were removing. And actually, when we remove this set of nodes, system was very so here system was disrupted. So what was the size that we want to bring a system down to? So the red color is describing the algorithm that is removing nodes. So on x-axis we are having the cost of removing nodes. So at final stage, so we are using 40% of our budget, and with this 40% of our budget, we have bring the network to the 80% of its original size. Okay, so when we remove this subset of nodes that are red, we have now we have a network that is 80% of its original size. Now we also tried to account for, of course, a cost. Of course, for us can be also like a degree-based cost. So it assumes that, like, if you're removing certain node, that it is actually much harder to remove a node that is better connected. Okay, and then we are having different strategies, and then we see that the one that was previously state of the art, now when you take into account the cost, now you see that it's not that good. Why it's not that good? Because we could find much better solution with our algorithm when we are taking this cost into account. Okay. So how to formulate this problem in a mathematic way? I will not go into details of this formula, but essentially what we are having is some kind of a matrix that is called Laplacian Matrix. And this Laplacian Matrix is actually describing the structure of a graph. And by looking at the spectrum of this Laplacian, we are able to do the partitioning of a graph to few components. So of course, this thing was known for a long time, but what we did is actually we have used a special type of a weighting such that we include cost of every node into this Laplacian. And then we call it node-weighted Laplacian, and then we proceed with spectral clustering. So in principle, we take some adjacency matrix that is described in the network, we add weights, then we construct some linear algebra matrices from which we are able to do the partitioning of network to multiple components. For example, if you're taking an airport network into consideration, so what would be the problem here? You want to, for example, reduce the air traffic in such a way that epidemic cannot spread above some level. So here we, for example, have said that like we want to reduce by 20% the original size, okay? And here we are showing that like with these two different strategy, MinSum was the previous one and GND is our strategy, is that we can have much lower cost. So in this way, it means that actually cost would be that the flux of passengers that are affected, and actually it is connected directly proportionally to the amount of money that you need to invest in some kind of economic quantity. So in the figure up and figure down, you are able to see area of a node is proportional to its cost of closing certain airport, and then you can see the previous method, and you can see how much it takes to how much cost it takes just by looking at it visually at the picture, because you can look at the area of the curve. So here you are, by just visual inspection, you can see the area. A human eye, it's very natural to see the area, and here you can see that the area is much lower, and here is the area that we are using. Okay. This is the paper. You can go and look at the more details. It's called Generalized Network Dismantling. It was published in Proceedings of National Academy of United States of America. And yes, you can find more details. So for next topic, I will just show you first motivational figure. This is some kind of a circle embedding from Escher. It's a wood engraving. And it's actually engraving that is showing some kind of, or has a resemblance to Poincaré disk. I will tell you why it is connected to the following paper. So the idea that we published actually this year at International Conference of Learning Representation, the paper is called Low Dimensional Manifold Embedding of Directed Graphs. So what is the problem? So we are having a graph, and we want to, for every node, we want to assign we want to embed it. It means that we want to assign either coordinates or something else in such a way that we somehow preserve the properties of graph. So what we have decided is that we map two probability densities. So now instead of assigning, for example, two coordinates for a node, we assign a Gaussian. So for example, we assign certain Gaussian probability distribution to every node. How we are measuring now distances between distributions, now we can use divergence. Divergence is one statistical measure that has connection to information theory, and it's actually telling us what is some sort of distance between these two distributions. Why I'm saying some sort, because it's actually not symmetric. And actually that is the thing that we want to do when we are talking about directed graphs, because directed graphs are having distances that are asymmetric. So imagine you have the following graph, and in this graph you are having different groups of nodes, each denoted with its own color, and you are having directed edges. So if you would just assign, for example, coordinates to every edge, to every node, then if you would just take Euclidean distance, it would be asymmetric. But as you can see, for example, from this node blue, there is a distance 1 to this node, this green node, but vice versa, the distance is infinite because you cannot pass in this direction. So by using probability distributions, actually there is quite a nice part of mathematics that was mathematicians in 60s and 70s developed. It's called statistical information geometry or statistical manifold theory, where actually you're having your geometry, but for measuring some kind of a metric inside, you're using now Fisher information metric that is connected to this divergence. So now when we embedded this graph to probability distributions, in particular to the Gaussians, we can now show where they are lying on some kind of geometry. So this is kind of an underlying geometry. As you can see, this geometry is a little bit curved. it means that like distances are not anymore straight lines. And then, of course, what we show is that this type of embedding is actually preserving more properties of directed networks than the previous methods for embedding. Inko, can you just confirm up to this point, is the voice also okay?
Yes, still rocking it, you know.
Okay, thank you. So now I will just pass to Bitcoin. And Vinko, can you also tell me, so we need to end the presentation in 10 or 5 minutes. We have also questions.
Well, yeah, you may proceed as you like. We have this session open for another half an hour.
Okay, so we'll then do a little bit less than 10 minutes, and then we check what's happening with questions. Okay, so the Bitcoin. I will not do too large introduction to Bitcoin, but in principle, it is just like decentralized pay-to-pay systems that is happening over a distributed system. When you need to pay some amount of money to someone else, someone needs to sign it. It's connected to certain cryptographic protocols that have connection to elliptic curve cryptography. But what is very interesting for us is that all transactions are written to blockchain. And it means that, for example, we could analyze all these dynamics. So in a period of time when we were doing this paper, we analyzed all data from blockchain from 2014 to 2017. We tried to analyze the evolution. Okay. So now what are the nodes in this Bitcoin network? So imagine now I need to pay a little bit of Bitcoins to Vinko. Okay, so what I need his wallet address. So if he gives me over a chat this address, I'm able to send money. Then people in background are going to be confirming this transaction when enough number of people, when enough number of confirmation has been done. This is written to a block and then stored to something that's called blockchain. So a large binary file, and it is always somehow relating to the previous blocks. But essentially, this is telling you that one address is sending some amount of money to a different address. So what we are having a network that is temporal. So every day we are having a different network, okay? And the edges between these nodes, they are actual amount of money that is being sent on certain day. So what we did is actually we did the aggregation, daily aggregation. So now imagine that for every day you have one snapshot of Bitcoin network, okay? Then what we can also do is we try to connect some nodes together. Why? For example, in Bitcoin, you could have multiple accounts, and then you could use it like in 2 accounts, so to your wallet as inputs to the same transaction. If this is what happens, then we have a large, some kind of a confidence that this is the account from the same user. So in this kind of a way, we can also aggregate from additional addresses to user graph. And then we start with this user graph where user is defined as all input wallets that were somehow that were used within same inputs. And then, for example, if I'm having 3 different addresses, A, B, and C, in first day I'm using A and B together, second day I'm using B and C, it also means that A, B, and C are connected. Okay, so now when I have described what the nodes are, these are the users of wallets, so set of wallets. We just take this graph, which is more or less just now adjacency matrix, which describes you who is connected to whom. Okay, and now what we can do is like instead of taking, now we want to apply something from machine learning or something from data science or from signal processing. So we now take the whole graph, which is a matrix, large matrix, millions of users, and we just stack them and make a vector from it, okay? So we are just taking all somehow enumerating all these things, and out of the matrix we make a vector. So now every day dynamics is described with certain vector, okay? And now if you ask me, now I show you like one matrix X. If I'm analyzing 10 days, then I will have here 10 columns. If I'm having 1 million users, I'm going to have here how many rows. Actually, it is connected to the number of possible edges. So we are just somehow enumerating edges, and then every row is connected to one possible edge. For example, if on day 1 I'm sending 1 Bitcoin to Vinco, then on this edge we will see 1. Okay. Second day I'm not sending anything to Vinco, so there is 0. Third day I'm sending again him 1 Bitcoin. I don't know why, don't ask me, but for some reason I'm sending. So this is the explanation of this 1, 0, 1. And here, for example, can be an edge that is describing to whom Vinco is sending money. So on the first day, he's sending 2 Bitcoins, second day 1 Bitcoin, and last day 1 Bitcoin. I also don't know why Vinco is sending that amount of money. Okay, and now what we can do, we are having this matrix. And instead of talking about this large matrix, let us just now try to somehow find some kind of signals inside patterns that are low dimensional. So what we can do, we can say, okay, let us now approximate the original matrix X with multiplication of 2 matrices, for example, W and H, okay? And then if we are able to find these 2 matrices such that when they are multiplied, we get some kind of approximate X, then in this matrix H, we would have actually the patterns that are showing us the embeddings of this dynamics. Okay, so in principle, this is the objective function that we are having. This is actually matrix norm. And just like a visual interpretation, what does this mean? Is the following. Imagine now you are having a graph that is composed out of different colors on edges. And if I have found three different patterns inside, then I will represent my graph as linear combination of these 3 subnetworks. So my graph then is going to be described 1 time weight of this network plus 1 time weight of this network plus 1 time weight of this network and plus, for example, 0 weight of something else. Okay, and then with these 4 numbers, 1, 1, 1, 0, I will have a representation of my graph that is large with just 4 numbers. So I will say 1, 1, 1, 0. This is the representation of graph. Okay. And the idea is somehow that we try to use now this representation of graphs for a certain day, and we try to learn, can we try to predict the volatility. So what is the volatility? Volatility is actually how prices are moving on a market. So we try to see whether in this kind of patterns of this matrix H that we have found, this matrix, so the number of columns here is exactly to the number of days that we are having. So if we had 10 days, here we will have 10 columns. And we are just trying now to combine them to describe the volatility. Okay, and then, for example, this is the real volatility. And then we are doing out of sample, trying to do some kind of a prediction of the volatility from structure of graph. And this is the signal that we are getting. Of course, now we should be able to measure how good this is. And usually this is in signal processing, measured with something that's called receiving operating characteristic that is having true positive rate here and false positive rate here. And actually this is with respect to predicting whether the volatility is above some level for next day. So based on a structure, we are trying to predict whether the next day volatility is going to be higher than some threshold. And then we could be changing these thresholds. And when we are changing thresholds, we are then getting different parts of this curve. The details are written in this paper, inferring short-term volatility index from Bitcoin blockchain. These are other papers from cryptocurrency markets that I was involved with. I will not go into more details, but just in a minute. So for spreading processes, because somehow it's interesting. So this is one engraving from Boccaccio's novel around the Great Plague of Florence. And the idea is that we are trying to model spreading, which kind of spreading, for example, something like susceptible infected recover spreading. So when susceptible people meet, so when susceptible infected meet, he can get infected with certain parameters, beta and gamma. This is what is describing the dynamics. One of the papers that we made was this called Simulating SR Processes. You can see more details here, but the idea is somehow that for a graph and parameters of spreading, we are able to get the weighted graph, which and we are assigning weights to this graph, and then we have one nice property. And this is the property that's denoted with this picture. So here we are having clocks. So now when you take a shortest path on this graph, this shortest path actually has equivalence of time. So if shortest path from some node to a different one is 20, it means that there is a 20 units of time that spreading needs to travel from one node to a different node. There is also one new work that we showed how to unify susceptible infected recovery processes and networks with this type of methodology. This is the collaboration with UCLA. And at the end, I would just try to tell you and advertise Epidemic Datathon, which is actually a real-time challenge where we are trying to predict what is happening with COVID-19 for next 7 days, 2 days. And if you visit this website, you can join and try to help us in doing real-time predictions. And at the end, I would just like to show also like a connection to a startup that we recently did. So it's called ISOT. It stands for AI, Signals and Operations in Trading. So how we use state-of-the-art research and technology to produce signals from raw data. So we are trying to deliver these signals to our customers. Customers are like financial institutions. For example, this is real-time prediction of volatility. So what's happening with risk on Bitcoin market. And then like every minute we are doing a prediction and updating it. And we are giving it as like algorithmic signal to financial institutions. Who is this? This is a team of former colleagues that are using machine learning, business skills, data science in order to create this signal. So we have one co-founder, which is CEO, that's called Stefan Klauser. We have me, and we have Tian Guo, who is our head for machine learning. And we offer more accurate estimates and innovative signals for financial markets. This is our address if you need something. And here I'm ending. And Vinko, this is the end of a talk. So please, you can maybe open a discussion.
Oh, thank you very much, Nino. This is a really nice overview. Just a pinch of everything to get you interested in the topic.
Yes, can you just please with microphone just to hear you better?
Okay, getting back to the microphone.
Yes.
Okay, so we have 30 participants here, and you can all ask questions. You can speak openly, or you can just write a question between the Q&A session. I will read it out to the speaker, or just feel free to drop your voice. So, apart from these 30 participants, like 500 social media who at least accidentally see the video part. And I guess this will rise over time.
Vinko, I haven't heard you. Your microphone was still.
Okay, end of the working day, I guess, so we are lacking of energy as well.
Okay.
So apart from the participants in this call, you have about 500 people who at least accidentally hit the watch the video button. And this part will rise, so you will stay on forever in this digital archives of ours. Okay, so in the meantime, while we are waiting for questions, let me ask you the first one for my part. Well, the big question is, how do you obtain the dynamics of some process? How do you describe it with mathematics for the first time? Say, for example, if you are talking about virus or whatever, on the general part where you introduce that derivative, something, how do you obtain it for the first time?
Okay, that's actually quite a good question. So the question is, how do we estimate, how do we know the modeling dynamics for a spreading process or any process? So actually, first I will answer in general, and then I could relate directly to the COVID case. So ideally, you would want to build some kind of, either from theory, some kind of models that are microscopically, you're trying to define what happens with epidemic spreading. So what can happen, for example, with epidemic spreading? You could say that someone can spread some disease. Okay, then if you want to describe or have these dynamics written with some mathematical formulation, at the beginning, people started with differential equations. So you try to pose a lot of assumptions such that you are able to write these differential equations. And then you are having a certain number of, let's say, breakthroughs, because with this powerful tool, you're able to understand a lot of around epidemics. For example, long-term behavior, criticality, when it's going to spread, when it's not going to spread. But then there is a question. How do you find these parameters? And then usually you would need data. Then what you need to do is like you need to fit this data to real process. And then of course there is a question whether this is whether this, although you did fit, whether this is a good representation of process. And actually this is the reason why we are also running this epidemic dataton, because we are trying to see which models are able to actually predict, let's say 1 week, 2 week time accurately, with uncertainties, what's happening with certain dynamics. So I would say that it's like, in general, it's not easy, but I just gave you the flavor of it.
Okay, thank you. So is this, let's call it big data, is it a prerequisite, or can you do some of the physical approach in some cases? Sorry, my microphone again.
Yes, can you repeat the question?
Is big data always required, or can you lean more towards some kind of physical phenomena? Well, I guess physical phenomena is less interesting because you are doing these social complex networks and so on.
Yes. So the answer is the following. So of course, like you don't need to rely on data, but then the problem is, like when you construct this model, how will you verify is it good? So it has to preserve either some kind of it needs to show some properties of real world process. At certain point in time, you will have to meet the data and try to explain this. Your theory needs to explain something that's happening in reality. So I would say that how you are constructing model, it can be data driven or model driven, but in the end, still it needs to respect and describe reality.
Okay, thank you, Nino. So we have a comment from Alexander to send the participants the video recording and slides of the presentation. Yes, it will be available in our YouTube channel, so you can drop by anytime. I will also send you by email. Okay, so Robert is saying that he does not see 30 participants. Yes, Robert, that's because of the WebEx way how to cope with many people. Yeah, you don't show everybody. So, okay. Well, we don't, but if you have any questions, just try to speak out loud.
People can unmute the microphone by themselves, or?
Yes, it should be working like that. Manuel, can you confirm that from your part?
There was something on a chat.
Okay, I'm just trying to figure out whether you can talk. You can just confirm this.
Yes. Vinko, there is one question from Matija Mikac. It was sent, but it was privately. He didn't. I can read it out loud.
Okay. So.
Okay. He said, like, you walked through the results of BTC example quite fast. Could you say more about the prediction results you obtained in the period of 2014 up to 2017? Yes. So the problem was, can we somehow try to predict some parts of the volatility for next day? So it's a daily volatility, price volatility, based on a structure from a previous day. And it was made as binary prediction, meaning whether or not volatility is above some level. And what is happening actually is that we saw that in the first period from 2012 to 2014, this prediction was better. So here, statistically, if you are like random, it should be here on a diagonal. But in the second period, when you're taking everything into consideration, you see that this is like a little bit lower, but still above the level of noise. But usually, yes, a lot of financial markets are quite noisy. To a certain extent, up to some period of time, we tried whether there are some clues of the volatility that can be used from the prediction from a structure, and we saw that yes, the answer is yes, there is something inside. But what we also noticed that actually a lot of trading is actually happening and not written to the blockchain. And after some point in time, this is also partially maybe the intuition why it's not describing to the full extent volatility after some period of time. So here we are showing that traded Bitcoin divided by the Bitcoin volume in blockchain. So at a certain point in time, you can see that order of magnitude more it was traded inside of exchange offices than the volume that was written to a blockchain. Okay, so I think that was like, it says thanks. Okay, and you can read more here in this paper. It's also like freely downloadable on archive. Vinko, do we have I'm seeing some question from email, but do you want to read it, or there is another order how to go with questions?
Oh, it's okay. So Nino is in short asking what is the best way to start as a data scientist? What are your general recommendations to the new people in the field?
Okay. So I would say so it depends on your background. But at the end, data scientist, I see a difference between data scientist and machine learner. So machine learner is someone who is developing algorithms. Data scientist, he's using algorithms, understanding them, and he also knows the domain. So there is a bit of difference between this. So I would say that this is the reason why machine learning is more mathematically driven, and data science is somehow using it, but still you need to understand things that are happening in background. This is at least my definition. So what is needed, as a general rule of thumb, you need to understand, it depends which kind of data science do you want to do. So if you're having certain background, you just need to find which part of data science you want to use. So is it like statistical methods or some kind of a different methods? And I would say like statistics, parts of machine learning, and in general mathematics is quite useful. So statistics, linear algebra, and probability. So this is somehow the things that are like pre-requirements, I would say, for being able to be a good data scientist.
And Nino, also, if you're a researcher, the always best way to start doing something is reading what is already been done in the area. And lately, this is a really hot topic, so that you can find online lectures on Coursera. And also, IEEE has what we call a learning network, archives of lectures and workshops about the particular topics. So try to find there as well. But as Nino mentioned, I think, well, in our experience as well, coming from our professional background, we just spend a lot of time talking with the people who are very proficient in certain domain and try to form their vision into some kind of mathematical way. This approach works so you can, retain your knowledge of the general mathematics, but not spread your hands to the different area. It's not easy. It takes, let's say, 1 to 3 years to learn about the domain, but that's how it works, at least in our case. Nino, I have one more question since we are talking about machine learning. And I mean, it's a really great topic. People are talking every day about artificial intelligence. And
just to tell you, so my core, I'm not like considering myself as like machine learner.
yeah.
I'm like customized to a lot of things in machine learning, and I'm do publishing. But I would say that how I'm seeing myself, it's like this interface. So using it as a tool and sometimes also developing it. Yes, but please.
Yeah, that was exactly my question. How do you relate machine learning and complex networks? So you gave a part of the answer already. And
Yes.
what is the advantage of this approach? Complex networks, so I would say it has a larger degree of physicality than just simple machine learning.
So I would say it depends like what are kind of things that you want to do. So if you're just using some method that is black box, then the amount of insights that you can get is also somehow limited. If you're trying to do some kind of a modeling, you can try to get more insights. Statistical machine learning, statistical learning theory is giving you also like quite powerful tools to understand these topics. And actually, a lot of physicists are doing major contributions and having major contributions in physics. And actually, a lot of new machine learning contributions are inspired by physics, like statistical physics. Yes, so I would say that a lot of now things in complex systems are being upgraded by certain novel innovations. You can look at it either as like a new numerical algorithms. This is one way of thinking around it, or you could think it like also if you are studying in depth what it is happening, then it can somehow also give you more insights around systems.
Okay, thank you. We have another question. Do your models offer a way to find out the inner structure of the processes you investigate? And can you comment that a bit?
So can you repeat one more time?
Do your models offer a way to find out the inner structure of the processes?
Inner structure of processes. So in order to try to answer a question, I will try first to understand the question. So structure of processes. So somehow, okay, let me try to go, for example, to the spreading dynamics of epidemics. So usually this is described like you have a graph, population of people that are connected with edges, and then when they meet, they could spread a disease from one to another one. So if you are having, so the question was, can we find out something around the structure of the process? So in principle, yes, but I cannot say that like it's that easy to generalize these things. But if you are able to describe or fit this dynamical process, then you are also able to see whether some things like certain interactions are needed or they are not needed. Imagine that you are fitting like a model, and now you're having dynamical process that is having a lot of parameters, and then at the end you see that you are having only sparse representation of the parameters that are needed. Somehow this can then be an answer to your question. Yes, you can find out something around the structure of process by doing this kind of models. I don't know, did I answer the question?
It was a question of Robert. So Robert, if you have more comments, just please write it down. But Nino, since you're already on this slide, so I see exponential functions as transition between the states.
Yes.
Can you apply in general some kind of nonlinear transitions among your states, or is this just has to be certain properties like exponential function in this case?
So that's a good question. So your question is why are we having here exponential functions, and can we have something different? Okay. And then you also mentioned something around linearity and nonlinearity. Exponentials are nonlinear, to a certain extent why we are having exponentials. Because when first people that tried to model the dynamics, they wanted to use the tools that they had to describe it. So they used differential equations, and somehow natural explanation when you write down these rate equations is that, for example, if you are having a rate beta that when susceptible means infected, that he will become infected, so that is a spreading. So if you are saying that when you're writing these differential equations, you are having a beta rate. So then this beta rate is actually, from probabilistic point of view, described that in dt time, infinitesimal time, you are having beta dt probability of doing the transmission. Okay, and then this is easing down a lot of things in numerics. First, the exponential is very easy to derivate. It has a natural interpretation. It is Poissonian process. It means that it's also, in this case, it doesn't have memory, which is also nice. Processes without memories are easier to describe, so they're like Markovian. And then when you're talking about, usually in these systems, you're not talking linear, nonlinear, you're more talking Markovian and non-Markovian. And non-Markovian is implying that you are having memory, for example, in recovering. So to tell you, like everyone now, or a large majority of people, for analyzing recovery of patients from COVID, they are to a certain extent using exponential formalism. So this is gamma e to the power of minus gamma t. This is describing the density when someone will recover. Okay, and now if you plot this thing, this distribution, you will see that it is like something like this. And somehow it's not having a characteristic spike, which is describing the mean thing. And most certainly, when you're analyzing this, it is actually saying to you, when you're looking at some time, if up to some time you haven't recovered, it means that you will also, it's not, so your history is not relevant, only its current state for recovering process. And you, of course, you can now see that somehow naturally this kind of Markovian property that you are not having memory is not true, because for your recovery process, for example, you have to pass certain number of stages for immunology, etc. reasons. And then, of course, then you cannot use this exponential distribution because actually it cannot describe non-Markovian or some process that has memory. And that's actually one of the things that a lot of people are like just using it because you have a momentum of using it. We have tried to, for example, generalize this recovery process here. And for example, you can specify different distribution for recovery, something that's like Erlang distribution or like negative binomial. And then it would describe like recovery in a more realistic way.
Okay, thank you, Nino. As you see, my background is not really in complex networks, but we do mostly differential equations, rather either linear or non-linear. So this is a little bit untargeted question, but we are really challenging.
So let me try directly to answer. So usually I don't have it now written, but so this SAR process with certain assumption is written as nonlinear differential equation. Okay.
Okay.
But you have to have an assumption on homogeneous, let's say, homogeneous connections. So then you are having something like this derivative with respect to time of, for example, susceptibles. Susceptible is like proportion of the people that are susceptible. That so this is on the left-hand side, the derivative of this susceptible variable. It is decreasing with minus beta. Then you have interaction term, number of susceptible numbers times of infected. So this is the first equation. So this is, and you can see now here that you are having S times I, which is having an interaction term, and that's the one that is making it nonlinear. So the most simple explanation for SR process is already having a nonlinear term.
Okay, that's very good. And it's really a powerful tool how to present this kind of processes, because in general, you're having a lot of headaches about it. Okay, Nino, thank you very much for your answers. So far, we don't have any more questions. We have just a thank you for Robert for your previous answer to him. That's it a little bit from the audience, I would say. So I wish you, Nino, good luck with your endeavors in future with your company. That's really nice applications and a really bold move. So good luck, guys, with that. And for the closure, what would you like to say for the, let's call it, future generations of complex scientists?
Learn mathematics.
Yeah, it's a hard one.
Yes, everyone needs to do it.
Okay, well, thank you very much for your talk. It's been a pleasure.
No problem. It was a pleasure. Thank you for the invitation. And thank everyone for participating and asking interesting questions.
Okay.
Okay.
Well, I'm shutting down the stream. So that's it, right? We are not
So I can
online
also
anymore.
stop it. Yeah.
Yeah. So okay. So as I see, you have a lot of, well, you have like in different countries of the participants. So it's a really nice geographical spread. I guess that's.
I'm again a microphone. I'm losing your microphone.
Sorry. Okay.
So the streaming is finished, yeah?
Yeah, streaming is finished. We are still in the chat. We have a number of participants are declining slowly, and that's it. So what I noticed is just you have at least 15 countries here participating. So that's very nice. It wouldn't be as easy to get it apart from the online version of talks.
Okay, let me see a bit chat. How did you like the presentation?
Me personally, I find it really interesting. We are trying to, well, to do some kind of modeling in logistics lately. So I see, well, we were
this Robert was having problems with audio. I'm now reading.
Yeah, but we can fix it.
Yes, okay.
So logistics seems to be very hard to model, but I think your complexity approach is very worth to go into, try to figure out something.